Yeah, welcome everyone for cloud computing and big data. Welcome to the online audience today. We don't have something in room today, but we have an invited speaker, Chadi Barakat, that will talk about, lecture 11 material about big data analytics and cloud data mining. So Chadi is a real expert in these topics, and please introduce yourself, Chadi. Thanks for coming today.
Yep, thanks for having me. My name is Chadi Barakat, and I'm doing my PhD currently with Morris, but in bioengineering. Stay with me for a while. I know as a bioengineer, I'm going to talk about applications in retail for a bit. It's okay. Don't. I'm not going crazy. We'll get to what that means in the end. But yeah, my experience so far has been in my second year of PhD, I've been working on several projects with the Forschungszentrum Jülich in Germany, and as part of the IHPC, the Icelandic HPC community. And also we have been working on a lot of projects in retail and in the medical field as well. So there's a lot of applications of deep learning and machine learning, association rule mining, all of these using cloud resources and using the available resources at the Jülich Supercomputing Center. So with that experience, I think I can maybe share some of my experience in the field and also my knowledge about the intricacies of this stuff. So yeah, I hope that my input in this case would be very helpful for you, and maybe some guidance for your future, and maybe some things you can apply in your own studies.
All right, yeah, so then I think it's time to review a little bit the last lecture before we come to the material of lecture 11, which I will take care of briefly before Chadi then starts with his presentation. So if you remember in lecture 8 to 10, we really had lots of conceptual topics. So this was necessary because we started in the course very quickly with, basically lots of material related to practical examples, to the assignments. So, and we left out lots of considerations and fundamentals really of cloud computing that we actually now manifested in lecture 8, 9, and 10. And the last lecture really on lecture 10 was then this SAAS level, and you see here on the top left again, the idea of using now, compared to the infrastructure as a service elements with the bare metal hardware and virtualization. On top of that, these platforms, these components we can reuse to build cloud applications, and all of that together as a really custom experience, as the experience of using an application as a software is then basically the highest level, so to speak, of the cloud computing approaches, which essentially means just swiping the credit card and you essentially get some service of sorts. We have seen there are different ways how that is actually used today. A very profitable business is the ERP and CRM business, so customer relationship management and enterprise resource planning. There are different tools. We had the Zoho example, but also there's Dolibar, there's many others these days, and also for project management, you're thrown at basically different solutions from different vendors. But they all have in one way or another the same idea of operating. If you come to the right-hand side and see essentially this kind of horizontal scaling ability that they have, of course, always still their key, let's say, hardware is, of course, physical, right? So there is a real infrastructure underneath, but you as a user don't understand that anymore, and you don't need to understand it. But what you want to have is, of course, a software that scales very well, that is, really performant when it comes to many users. So basically on top of this infrastructure as a service, you want to have a virtualized environment that is very quickly scaling up and scaling down to the number of users. You don't want to click somewhere in your software and suddenly it waits for the internet and waits and waits, and you cannot proceed with your application, right? You pay a lot of money for these applications usually, monthly fees, yearly fees. We have seen different models in the last lecture, subscription fees. But essentially what you then can expect is to have a very good performance, of course. And how the way they do this is really to horizontal scale, you see in this graph. So you add more physical resources, perhaps, and then let's say new layers of virtualized platforms in order to have essentially different virtual solutions in these different softwares. Now, we also said here as an example, virtual solution A, virtual solution B, there could be different reasons, there could be different operating systems, you have maybe something what you want to do for there. But here in the cloud, this is maybe not so, on the software as a service important for us. Here, virtualization can be much more better used, for instance, in versioning of software. If you remember the last time I said A/B testing or having, let's say, a research version of the software in the cloud available for trying out new features. So you have exactly the same cloud service twice, but one is the production one that is basically for the real end users, and the other one is just for testing new features, having, let's say, some friendly users that have been a long time maybe subscribing to this, testing this platform before it becomes and rolled out into the production version. And this is a very common paradigm where many people in the software as a service oriented world work with. And here just more examples. I mean, Zoho was one idea where I said to you, I have personal experience that it's running very well, although I'm not paid by them to say that. I'm just using it now for many years, and it's a very, very stable, very production version. We have Amazon SageMaker as a machine learning tool, which is really powerful. But of course, indirectly, you have to pay the infrastructure that you use with it. You have the subscription fees there. They hook you with free hours. But once the free hours are gone, of course, you also have to pay. And when you then want to have a cutting edge deep learning network, you have seen in Rocco's talk, you go there and of course have to pay the price for it. With lots of, $28 per GPU hour potentially. And still, we also had as one example, the CRM applications, where I also wanted to raise a little bit awareness of data protection regulations. I'm not an expert there, just to give you hints that, the Patriot Act means in the US, you can actually always look into the data of Europeans if the data is hosted in the US. We have seen the Safe Harbor Agreement or the discussions around it. So this is not at all clarified. I mean, there are lots of rules in basically existing, and lots of it is enforced in Europe. But when it comes outside Europe, many things get unclear. What happens if you have your user data in Alibaba? What happens if your user data is in the US? So it's all not really clarified. And then finally, also to give you awareness of data protection and raising awareness that machine learning is everywhere used today. We said, with one click, you get the social media blueprint from one person in these tools. So if you have public profiles, if you make, have lots of things on the web, chances are that people that hiring you maybe are not officially allowed to look at this, but they can, right? So always remember, we're living in a glass house world these days where many things are just one click, and there's some application like Freshworks here. If you do this, or Zoho and so on, they have really powerful tools with machine learning looking in all what you shared online and stuff like this to know, of course, you as a customer, right? That's the key idea of a salesperson that using these tools. Anyway, so to make you not afraid, I think many lawyers working on this, and largely GDPR helps us a lot already in Europe, but it's not perfect. As also Chadi knows from here and there from medical domains, it also has its problems, particularly also if you want to use the data maybe for some good purpose. But I think that's all I say for this lecture 10, and Chadi, take it from here. Thanks again for doing the lecture, Chadi.
Okay, thanks, Morris. And from there, we move on to just a brief outline of the lectures themselves. And we are, as we all know, it's lecture 11, which is mostly big data analytics and cloud data mining. So this lecture is going to be mostly divided into two parts. Of course, the two parts is again divided into two parts, but the second part won't take that long, don't worry. But the first part of our lecture is going to be about association rule mining and its applications with big data. The second part will be more about deep learning, which is being used as a tool to generate data, or if it's not generating data, at least analyzing the data. But in our case, we're going to be generating data. So in both cases, we're going to go into the details of what each approach entails, what are the most common approaches from this one, the common applications, and also how it can be applied within the cloud. So let's start off with just a brief explanation about association rule mining. So if you've existed in the last 10 years at least, you know how the internet is, and you've bought something online, of course. And anytime you buy something online, the first thing that you get is customers who bought this frequently also bought X or Y or Z. And this specifically is what association rule mining is. It tries to create a connection between two products that people usually buy. So when you buy one of them, you're probably likely to buy the second one. And to do this, it's a set of algorithms, sometimes done by people and sometimes done by computers, to uncover unknown relationships between one product and another, one product and a bunch of other products, or a bunch of products and a single product. To do this, the rules are created based on a set, a number of frequent item sets, and these highlight these uncovered relationships within a specific data set. But to be able to do that, you have to have a given data set. You cannot apply this to data that you do not have, of course, because your algorithm needs to know the items that you have and then come up with the relationships between these items, and then understand how these transactions are happening to highlight which relationships are okay and which relationships are not. So the approach that association rule mining algorithms usually use is an unsupervised machine learning approach. And I'll explain more about unsupervised machine learning in the next part of the presentation, but mostly it's, if I want to say it in a nutshell, it's mostly something that you're not involved in training. It's just making connections without your input, besides that giving data and then expecting something out of it. So there is, as I said, it's unsupervised, so there is no guiding output that you give the network or the algorithm to tell it that this is how you should be giving me. It's just doing its internal calculations, maybe as a black box, and the output comes out and you judge it if it's good or bad, but you do not have any direct input on how that output changes. There are several algorithms that we can apply in terms of association rule mining. The most common are APIori and FP growth. There's also Mafia we mentioned here. To be honest, I've never used Mafia, but I know that APIori and FP growth are some of the most commonly used association rule mining algorithms in the industry. So the data set usually that is given in this kind of applications is a transaction data set. And we'll get into what that means in this slide. So in this slide, we can see on this side here, a number of items in brackets. Each one of these is a single transaction. From these transactions, we can see that in 3 out of the 5 transactions that we have, there are the people bought diapers and beer. That's why they're highlighted in red. From this, we can extract a diapers and beer item set. This is called a frequent item set. It's bought in 3 of the 5 transactions. Based on this, we can infer that if you buy diapers, you are likely to buy beer. Technically, it's an accurate prediction. If you buy diapers, then you have children. Then if you have young children, you do not have the time to go out, party, or maybe go to the bar. So you stay at home. People still want to have a good time, so you buy beer. Makes sense. This is a basic one, but there are other deeper connections that we might not know. Bread and eggs is a normal connection, but you can see that it's not highlighted in these transactions here. So from these kind of transactions, from these kind of item sets, we can find out things about purchase history. We can find out things about interest in certain products, maybe seasonal interest, and other such information. And this is usually a very good way of maybe pushing one product against other products, encouraging its sales, and other such things that retail people do. But mostly you as a data scientist, it would be your job to find out these things and to tweak your algorithms to be able to create new interesting information. So this is one of the most famous retail examples, and it illustrates the basic rules. But this is a very small data set. So the challenge here is, how would you apply this kind of thing to huge transactions? In our case, which we will talk about in the next slide, we have a transactions list that has 2 million entries. In each of these transactions, there are, in all of these transactions, there are about 40,000 unique products and 100,000 unique customers. So the problem grows exponentially with your data. So to be able to do that, you have to automate your algorithms, as is the rule in almost everything in technology. When you can automate it, you can produce more results than any human will be able to do in more than 100 lifetimes. So with automation comes the benefit of identifying new opportunities for sales, as I mentioned before, and specifically cross-selling. In this case, diapers and beer, but in other cases, it could be perfume and face napkins to remove makeup, maybe a mascara and a set of earrings. It could be almost anything. In our case, one of the applications that we're using is part of the OnForOff project, which aims to improve or maybe bring the brick and mortar stores into the internet age. And as especially during the pandemic that we've all had to go through, these brick and mortar stores suffered a lot. So they have to have a new way of reaching their customers. And since they're kind of late to the game, it was our job to push them into it, push them to the internet, and try to improve their accessibility, their accessibility to their customers. So they've already done part of the job. They've been collecting their transaction data for a while as part of like the electronification of their data sets. And they have been sitting on this information for a while. So by making it available to us, we can actually help them more than they could have ever thought possible. So this lays the foundation of mining for association rules. If you don't have data, you kind of have nothing. So let's say you have a set of 2 million transactions. How can that help you? First of all, you can create transactions, you can create association rules based on the whole data set and find out the trends. But already these companies know these trends because they know what products sell. But what they don't know is if that changes from one city to another. And besides that, they don't know if that changes from, let's say, over Christmas, people buy more perfume, or over Easter, they buy more makeup, maybe. Maybe in summer, they buy more, of course, they buy more skincare products, but also maybe there's another spike that they don't know about. Maybe it's a small spike, but it's something that they can capitalize on. So this is one of the applications where we have been able to help, which is the small but relevant transactions that or association rules. And in that kind of stead, we can talk about the APIori algorithm, which I mentioned is one of the most commonly used algorithms for association rules. So from the previous example, we have this data set, let's say this set of transactions. And APIori is mostly an approach that runs through the data set on several runs, collecting as much information as it can about all of the possible transactions. So it does this recursively. It does this for almost every product, and then it does some pruning along the way. But to be able to do that, it has to create item sets. So first of all, it creates single items, checks out how many times these items appear, and prunes these products based on a given minimum support that we're looking for. It's mentioned here. This minimum support, if a specific product doesn't appear more than this minimum support, it's highly likely that this product is not really a common product that people buy. So based on that, we ignore them and we ignore all of their associations, and from there move on to the more commonly bought products. And from that, we create 2 item sets. And from that, again, we do another set of trimming. And from there, we go into the 3 item sets, where it's the items that are most commonly bought together, but in sets of 3. It could grow a very long way. And for every, it can go, let's say 7, 8, 9, maybe more. But the more you go, that means more iterations that the algorithm is running through the data. So I'm guessing you can see a kind of problem that happens in this case. But we'll get to that in the next 2 slides. But what's important here is that a priori, by running through the data in such a way, does a very good job at highlighting this information, highlighting how these products interact one with the other, and highlighting which products really are of no importance. In Python, one of the libraries that we most commonly use is MLExtend, which is the one that has applications of a priori. It also has applications of the next algorithm that we're going to look at. But mostly in this case, a priori itself, as a part of MLExtend, is very malleable. You can tweak it a lot. You can change a lot about it. But in general, the way it comes out of the box is a very good way of applying it. Of course, the least you can do in this case is to provide a minimum support, and your minimum support really depends on the type of data that you have. So if you have a very small data set, it wouldn't help you if you have a very small minimum support, because then all of your data is considered. And it wouldn't help to have a very large minimum support, because then none of your data is considered. So you have to do a lot of knowledge, know your data very well. Otherwise, nothing that you apply will work. And we had a lot of trouble with that, because a lot of the data that we had was completely irrelevant. A lot of the transactions were just single products being bought. And yes, that might be helpful, but also that kind of floods the information with unnecessary information or irrelevant information. So by knowing your data, you can trim out, as they say, trim out the fat. And also, you can highlight things or give them more weight when you understand how relevant they are to the sales of those products. So that means you have to be in constant contact with the client. And we forget that, but it's also at the other end, there is a client, and it's for their benefit. So you have to understand what they want. It's not just that you apply an algorithm and done, we can go home. No, you can produce some results. They will tell you that these are not good results. You can apply it again, produce better results, and then they could be satisfied. Maybe not. You can apply it again. So there's constant improvement. And at the same time, you know that they can't get to this improvement. You can't get to this improvement without their input, and they will never be able to use this information that they have without your help. So it's mostly working hand in hand. But in general, in terms of a priori, going back to this subject, we have a set of data, transactions and products being bought. And from that, we create a one-hot encoded matrix. The one-hot encoded matrix is a set of true and false values, Booleans, and one-to-one encoding. And I'm guessing you can see the problem that we talked about before, which is how much it grows when the data grows. So when you're mapping every product to every other product, if they are being bought together, yes, you can create a set of item sets, a number of item sets, but maybe that doesn't scale very well. But anyway, from those item sets that you have, we apply the a priori algorithm, and that algorithm, based on its minimum support, creates a set of antecedents and consequences. That is, you have bought Hugo Boss, for example, then you are very likely to buy Chanel. And on the other side, if you buy Chanel, you are very likely to buy Hugo Boss. If you buy all of these products, you are more likely to be recommended a Chanel product, and vice versa. So using these item sets that we managed to create and using the specific values of minimum support, we can trim this number of products that are given as antecedents and consequence. And also by reducing the support that you need for an antecedent to be relevant, you can also improve your output from the association rule mining process that you're doing. And then we get to the problem that we were talking about before. That is, a priori is a very effective method, but only for small data sets. When you take into consideration how large a data set can become and how large the calculations of that data set can become, you realize that maybe a priori is not a very good application in large scale, let's say, retail databases or maybe bookshops or something like that. So you kind of, yeah, as the data scales up, the problem becomes more and more complex and the computations more costly. And especially if you're using, as Maurice mentioned, if you're using cloud resources, it's costly in more ways than one. So even before the pruning and before generating the association rules, a priori is a very expensive algorithm, especially when it's creating this, one-hot encoded matrix, which if you just basic simple calculations, a 40,000 by 40,000 matrix can take up at least, I think, if I remember correctly, for us, it took 200 gigabytes. And no resource that you have locally can manage this kind of data. So from there, we go to FP growth. And FP growth is the other most common algorithm in terms of association rule mining. This approach is radically different from a priori after the first step, because of course it has to go through the data in the first place. It has to understand all of the products that are mentioned in the data. But after it does this first pass, it only does one second pass. And during the second pass, it starts constructing as they call it, a frequent pattern tree mentioned here. And this is the FP that we're talking about in FP growth. It creates this FP tree. And in that way, you kind of realize that the items aren't constantly being repeated. It's just interconnections within this tree that highlight which products are most commonly bought automatically. So the pruning is happening automatically while the tree is being built. So as you can see in this case, it's very clear that this kind of algorithm is efficient. It still kind of suffers from when the data grows, but at the same time, it kind of makes the best of the availability of the resources that you have. So that kind of makes FP growth a more likely algorithm to choose when your data gets to a large size. And this is exactly what we had to do. In our case, the same data set being applied in this case, you don't have to create you don't necessarily have to create, in this case, a one-hot encoded matrix. Instead, you can use sparse matrices. But anyway, FP growth itself doesn't have to go through that deep into the one-hot encoded matrix because it's automatically trimming the tree as it goes. And in this case, we can see that for the same data set, a priori and FP growth have completely different responses. A priori is immediately going into an exponentially increasing execution time, whereas FP growth slowly increases. Of course, it does have to take more time, but at the same time, the time that it takes is still within an acceptable range for us. The same goes when you decrease minimum support or when you increase minimum support. And in this, this is one of the examples where we were able to highlight exactly how FP growth is more efficient for our data set. But otherwise, we can also talk about the 200 gigabytes that no one really has access to. And from there, we move on to some cloud applications of these algorithms, because as you know, not everyone has access to. In our case, we have access to a supercomputer, but nobody really does that usually. And to be able to apply these algorithms for a business, even if it's a small business, you have to have access to some kind of resources. And one of these resources is, in this case, IBM Cloud Pak for data. It's a platform that builds on Red Hat OpenShift, and it's portable into the most commonly available commercial cloud resources like IBM Cloud, Amazon Web Services, Google Cloud, or MS Azure. And from there, these resources have, they give you access to all of the possible types of association rule mining that you can apply to a given data set. And also, there are other applications of association rules in the cloud. In this case, we're talking about FP growth via Apache Spark on Microsoft Azure. So all of the cloud resources already have their own approaches to doing association rule mining and simplifying the process of using association rule mining. So with that, we get to the end of the association rule mining section of our lecture today. But at the same time, it helps to know that in such cases, when you don't have access to high performance computing resources, you can access these resources, and you have to know which algorithms to use to reduce the cost on yourself and on your client as well, because in the end, how much it costs you to perform these algorithms is going to be very well reflected on your bill that you give to that client who asks you to do some job to them. So the cloud resources available right now through commercial suppliers are very malleable, and you can grow them as much as you want, or as much as you need, or as much as the money that you have allows you. But at the same time, you kind of want to make it as efficient as possible. So understanding which algorithm fits your application best is, in the end, directly related to how successful you are. And how successful you are is directly related to how well you can serve a specific customer, depending on the application that they require, of course. And with that, we get to the end of this section. And if you have any questions, I would be willing to answer them.
Yeah, thank you very much, Chadi. Very great lecture. I'm curious to see the second part of the lecture. So essentially, I would say we break here for 10 minutes, but as Chadi suggested, in the break, we can also have here and there some questions tackled if you're not filling up or refill your coffee.